Okay, what I want to do here is to demonstrate how to handle systems that have constraints and also how to handle systems that have high degree of freedom equations. And I'm not going to solve them with differential equations. I'm going to go straight to Laplace transforms. Hopefully you will believe that this is in fact the way to solve things. So let me start off with a real simple problem where you have two masses, and I'm going to anchor them together with a solid rod. So here's mass 2. So clearly when mass 1 moves, we'll put wheels on here so there's no friction. So there's really only 1 degree of freedom, because what you need is a position x1, and you'll automatically know position of mass 2. So if mass 1 moves 1 foot, mass 2 moves 1 foot, because they're connected with a rigid rod. And then what I'll do is I'll tie this guy down with the spring. You can put a damper in there, but for the point that I'm trying to make, damper doesn't really matter. So this is 1 degree of freedom. The order is also second order. So you can't get much simpler than this. Now, 1 degree of freedom means you'll get one equation. It will have one flow variable, and obviously that flow variable would be x1. But what I'm going to do is I'm going to say, well, I'm going to do something stupid, and I'm going to put 2 flow variables in here, x1 and x2. And you know what's going to happen, right? x2 is equal to x1, but I'm going to do that. The reason for that is because occasionally you'll have a complicated system, and it's just more convenient to write free body diagrams and write equations when you have more than the number of variables that you need. And then I'm going to show you how to get rid of them once you finish writing your equations. So anyway, we have these two guys, and I'm going to draw a free body diagram. So since I have 2 masses, I'm going to separate them off, and I'm going to put the masses separately. In this particular case, you'd probably be just as easy to write one free body diagram because really the 2 masses are in essence 1 mass because they're moving together. But anyway, I'm going to separate them off because I'm trying to make a point. So here's mass 1. Get the spring force. Step 1, I draw a line. Step 2, I write the equation. Step 3, I pretend like x1 is positive. If it is, it's moved to the right, and I pulled the spring. If I pull the spring pulls me. So there's my arrowhead. And then over here, because I have a rigid rod, I have a tension or a compression. I don't know which one it is. I'm just going to call it T and draw it in like that. Okay? And I'm not going to worry about gravity, etc. We already know that that doesn't make any difference. Okay, let's draw the free body diagram with mass 2. And I have T, which is equal and opposite. So I draw it in like that. So there's my forces, or my free body diagrams. Okay, so now what I'm going to do is I'm going to sum forces on each of these things. So we'll take mass number 1. So positive would be to the right. So I have T minus K x1 equals the mass that's in the free body diagram times the acceleration of the center of mass. Okay, and then for the other guy I have minus T. That's it. So that equals mass 2 times the second derivative of its position. Okay, now what I'm going to do is count the number of unknowns. I don't know T, I don't know x1, and I don't know x2. So the variables are T, x1, and its derivatives, and x2, and its derivatives. Now, I only have 2 equations. I have 3 unknowns. So now is the time to panic. But before I panic, these 2 things are both flow variables, but yet I know it's a 1 degree of freedom system. that tells me that I don't need both of these, that they must be related somehow. Now the relationship in this case is really pretty simple. What I know is that x2 equals x1. Right? There will always be, if you have more flow variables than degree of freedom, there will always be a constraint between them. It may not be as easy to find, but there is a constraint, so you know at least what to look for. So now if you count the number of equations, I have one equation here, I have two equations here, and I have the third equation right here. Okay, now, I'll ask myself, am I finished with this? Well, I'm not sure, because what I was expecting is one equation, and I was expecting second order. It looks to me like maybe I have three equations, or at least two flow variables, and I've got fourth order. So this is looking kind of strange. But since I have the same number of equations as unknowns, I'm going to try and solve it. So here's what I'm going to do. I'm going to go in here, and I'm going to identify the output variables for each one of these systems. Okay? So for example, if I look at equation 1, I see two variables in there. I see t and I see x1. I need to determine what this equation is solving for. Is it solving for t, or is it solving for x1? My rule tells me I should be solving this guy for x1 because it has the higher derivative. So that should be the output variable for this guy. If I had to name something, I would say, well, the t is probably an input. Okay, so for equation 2, I look at that and I say, oh, that guy is going to be solving for x2. Right? Or 2. And then for equation 3, I say, well, what is this guy? Well, I don't know. It's either x1 or x2. So I'm not quite sure what I'm solving there. But what the output variables are going to be is x1 and x2, not t. So anyway, let's draw a line here. Now I'm going to go in to try to solve these things them together to come up with this is what I'm expecting. All right, so here we go. First equation, I'm going to use the S equation. So I'm going to get t minus k x1 equals m1 s squared x1. Okay. Next thing is minus t equals m2 s squared x2. Third one is x2 equals x1. Now, what I'm going to do is solve these things algebraically, but as you've seen in other examples, if I don't have an external force applied to this thing, an external input, I'm going to get 0. Right? And the reason for that is because since I'm taking the Laplace transform, I have to include the initial conditions, but I'm taking all initial conditions to be 0. So if you look at this and I'm measuring from static equilibrium, and you say, all right, this system, how does it move if it has 0 initial conditions? Well, it's not going to move at all. So the answer is going to end up being 0. Everything's going to come up 0. I don't want 0. I want to find the correct equation. So what I need is I have to have an external excitation, something that will get this thing excited so it'll move. The easiest way to do that is to put in a external force. If you're pumping something, you put in external pressure or something. So you have to put some kind of excitation to make the thing move to some extent. So put it in, get your equations, and then you can take it out if you want to. But I'm going to put something in. So what I'm going to do is I'm going to come in here and say, oh well, and it makes no difference where you put it. So I'm going to put it right here. Okay. So what I've got then is the free body diagram. The change in the free body diagram is free body. So I'm going to have an external force action. How does that change the equation? Okay, you have an external force action. Okay, so what happens down here? External force action. You always have to have that in there. So if it's not drawn in, throw one in. And like I said, it doesn't matter where you put it. Just put it on, convenient location. Okay, so what I'm going to do now is I'm going to try and solve these equations. And to do that, I'm going to use Mathematica. So let me scroll over here, pull up my Mathematica. Here we go. And I'm going to scroll over and get my equations where I can see them, and create a new file. Let's see, we'll enlarge it. Okay, what I like to do is
Drawboard PDF window, apart, expanded.
I'm not quite sure what that was. So
Untitled 1, Wolfram Mathematica 10.0 window.
I don't know what's going on, but we'll see what's going on. We'll see if this works. So the first thing I like to do is quit, just in case I've been using Mathematica before. I'll define my equations. I have 3 of them. So tension minus k x1, 2 equal signs, mass 1 s squared x1. That's the first equation. The second equation, F minus tension, 2 equal signs, mass 2 s squared x2. Third equation, x2, 2 equal signs, x1. That's the last equation. Execute. You might look at that, make sure that it looks good. It looks good to me, so now I solve the equations. Since I have 3 of them, I have to specify 3 things to solve for. I'm going to solve for the tension, I'm going to solve for x1, and I'm going to solve for x2. Alright, so there are my solutions. I have, in this particular case, 2 transfer functions. One of them will be a transfer function for x1, and the other one will be a transfer function for x2. If you notice, however, they're exactly the same. So, but anyway, I'll summarize. Transfer function for x1 is equal to output over input. Output is x1, input is f. So the transfer function is going to be x1 over f. It's output over input, and that equals, according to Mathematica, it's 1 over k plus mass 1 plus mass 2 times s squared. The transfer function for x2 is exactly the same. It's probably no surprise. What is the if you were to say, what's the I don't know why it's not scrolling. If you're looking for the natural frequency, you take the denominator and set it equal to 0 and solve for s. And so you end up with the values that you probably would have expected. They're imaginary, and it's equal to the square root of k over the sum of the masses for both masses, which makes sense because they're tied together. They should have the same natural frequency. So in summary, what happens when you're looking for when you have multiple equations like this and you're using more variables than what you need, you always look for a constraint equation, which in this case was here, and then once you take your equations, convert them into the S equations, and then you just solve them as if they were algebra. So that's how you handle a constraint.